for joining our presentation on exploring UDTFs in PySpark. I'm Takuya, Senior Software Engineer at Databricks. And this is my co-speaker, Haejoon. He's also a software engineer at Databricks. Today, we will cover these topics about the UDTFs. So, what are UDTFs? Before we dive into user-defined table functions, let's first understand what a table function is. A table function is a function that returns a set of rows, essentially forming a table from a single input or a set of inputs. Unlike scalar functions that returns a single value, table functions are designed to return multiple rows. This makes them incredibly useful for operations that need to generate or transform sets of rows and from a single input. For instance, they can be used to generate rows from a range of numbers or to process complex data that result in multiple rows of output. For example, the range function in SQL or DataFrame API is a great illustration of table functions. When we use range 1 and 5, it generates multiple rows 1, 2, 3, and 4. Such functions are widely used for generating rows from a single value or handling complex processing tasks that use multiple rows of output. Understanding this concept will help us better grasp the capabilities of the UDTF as we proceed. Now that we understand what a table function is, let's explore user-defined table functions, or UDTFs, in PySpark. UDTFs allow us to define custom data processing functions that returns tables. This means this means we can write functions that generate multiple rows of output from one or more input rows. To pass multiple rows to a UDTF, we need to use a lateral join or table argument in SQL. The standard UDTF is available from Spark 3.5. The core components of a UDTF includes the UDTF class and the eval function, which processes the input rows and returns the output rows. Optionally, it can have the terminate function, which finalizes the output. For example, the eval function buffers the input rows, and the terminate function returns the calculation result from this buffer. Let's go through a simple example of a standard UDTF. In this example, we'll create a UDTF that takes two input values, start and end, and returns each value within that range along with its square. Class square numbers decorate it with UDTF decorator, and specially specify the return type that describe the output, the schema of the output. Inside this class, we implement the eval function, which processes the input range and yields the output. Now let's discuss the UDTF decorator. This decorator declares our class as a UDTF and specifies the return type. In our example, the UDTF decorator tells PySpark that the square numbers class is a UDTF, and that it will return us a table with two integer columns, num and squared. We can specify the return type using either a DDL string or a struct type object, as shown in the code snippet. Next, let's take a closer look at the eval function. This function contains the core logic for processing input rows. For each pair of start and end, the eval function iterates through the range and yields tuples containing each number and its squared value. This function is where you define how the input data is transformed into the output data. Let's see how to use the defined UDTF in PySpark. There are two main ways to use a UDTF, directly and by registering it for SQL queries. First, we can use the UDTF directly by calling it with the start and end values as literals. This method returns data frame object and allows us to immediately display the results using the show method, making it convenient for quick checks and testing. Second, we can register the UDTF to the Spark session for use in SQL queries. We register the square numbers class UDTF with a name such as square underscore numbers. After registration, this method integrates after the registration, we can use this UDTF within SQL, seeming to get the desired result. This method integrates the UDTF seamlessly into your SQL workflows, providing greater flexibility and ease of use in complex data processing pipelines. Both methods are demonstrated in the code snippets. So UDTFs have several capabilities that makes them useful for custom data transformations. They can handle complex data processing logic, allowing us to create sophisticated functions tailored to specific needs. For instance, UDTF can be used to aggregate data from multiple rows or to generate multiple output rows from a single input row. These features make UDTFs a powerful tool in PySpark for addressing various data processing challenges. While UDTFs offer powerful capabilities, there are some areas where they can be improved. By default, they work with a fixed input schema and data types and return a static output schema, which can be restrictive. This can pose challenges when dealing with diverse data structures. Adapting UDTFs to different use cases requires additional effort, and their extensibility can be constrained by this rigidity. Okay, then let's move on to the polymorphic UDTFs. Now let's introduce the concept of polymorphism. Polymorphism allows functions to process different data types and structures, significantly increasing their flexibility and reusability. In the concept of UDTFs, incorporating polymorphism means we can create functions that adapt to various input schemas, making them more versatile and powerful. The polymorphic UDTFs will be available from Spark 4.0. To make UDTFs polymorphic, we need to implement certain methods that enable them to adapt to different input schemas. The first step is to remove the return type from the UDTF decorator. Instead, we can define the return type dynamically when the analysis static within the analyze static function. The analyze function determines the output schema based on the input schema or its metadata. This adaptation allows UDTFs to handle a wider range of data types and structures, providing greater flexibility and enhancing their utility in diverse scenarios. Let's look at the detailed example of polymorphic UDTFs. In this example, we modify the square numbers UDTF to include the analyze static function and remove the return type from the UDTF decorator. The analyze function takes the same argument list as the eval function except for self, and dynamically determines the output schema based on the input schema or metadata. The arguments are of type analyze argument, and it returns an analyze result object containing the schema. This enables the UDTF to adapt to different input types and structures. The core logic in the eval function remains the same, processing the input range and yielding the squared values. But the result may be byte, short, int, long types according to the start argument type. Now that we've seen the detailed example of a polymorphic UDTF, let's understand the analyze argument and analyze result classes in more detail. Analyze argument is used as the argument type in the analyze function, providing metadata about the input arguments. This metadata includes data type, value, is stable, and is constant expression, which helps the function understand the structure and type of input it will process. Analyze result is returned by the analyze function and contains the schema of the output. It can also optionally include with single partition, partition by, order by, and select. These optional fields provide additional instructions for how the input and output data should be structured and processed. Okay, let's see the demo now. Please welcome Haejoon for the demo.
We can just end the show.
Yep.
Yes. Yeah. So I'm going to share a very quick demo for the PySpark UDTFs on the Python notebook. So let's start with the standard UDTF. So this repeat item UDTF takes two arguments, the item and the norm rows. And this UDTF returns the item as many rows specified in the norm rows.
Okay, let's zoom in here.
Sorry, one moment. Thank you. Yeah, so that is how it works. Yeah, and after defining the UDTF, we can simply call the UDTF directly using its class name. So we can see the 2024 is repeated for 6 times in the resulting data frame. And we can also call the UDTF in the SQL statement, or once we register the UDTF by using the spark.udtf.register function. So, and then the UDTF can be treated as a table from the SQL statement. So this also shows the same result with the above example. Yeah, and as the UDTF is treated as a table from the SQL statement, we can also use the UDTF from the lateral join clause. So we can see the joined result in the resulting data frame. Yeah, and next example is the count and max. Yeah, so this count and max basically takes a partition of an input table and returns the count of rows and the maximum value for the each partition. So we're gonna register this UDTF as well, and I'm gonna call this UDTF in the SQL. So basically, this query partitioning the 100 IDs by quotient divided by 10. So when running this code, then we can see the 10 rows, and each rows have an information for each partition. Yeah, and let's move on to the polymorphic UDTF. Yeah, there is some limitation of a standard UDTF. So for example, when I try to pass a string type of an argument to the repeat item UDTF that we defined before, then when I run this code, then we'll see the null string from the resulting data frame. Instead of the expected data frame I described here. So that's why we define the input type as an integer type instead of string or something. So in this case, we can use the polymorphic UDTF to dynamically determine the input data type. So instead of defining the return type from the UDTF decorator, we can add an analyze static method to dynamically define the return type based on the input data. Yeah, so now this polymorphic repeat item UDTF can handle the string type as well. So yeah, we can see the polymorphic repeat item here. Yeah, now the result looks as expected we want. Yeah, and the polymorphic UDTF also can be called in the SQL statement in the exactly same way what we did for the standard UDTF. So there's nothing special. So this is the last example. So the polymorphic UDTF can be also useful when we want to define a table function that take an arbitrary number of the arguments. So that means when we see this analyze part, then this analyze function can accept the arbitrary number of the keyword arguments, and this iterate the keyword arguments one by one and infer its data type here. And so I also register this UDTF. When we see this query, now we have two keyword arguments, A and B. So when I run this code, we can see the two columns A and B. And as we define this polymorphic UDTF as can take arbitrary number of the keyword argument, so we can add more keyword argument as we want with various data types, something like that. And this also should work. Then we can see the 4 columns in the resulting table now. Yeah, so that's it for the demo today. So I'm gonna leave it to Takuya again. Yeah, so for the conclusion, thanks.
Okay, thank you, Haejoon, for the demo. As we've seen, UDTFs are powerful tool in PySpark that allows for custom data transformations. However, by default, they have some constraints, such as fixed output schemas. Introducing polymorphism to UDTFs greatly enhance their flexibility and usability, allowing them to adapt to various data types and structures. The key takeaways from this presentation are understanding the basic concept of the UDTFs, recognizing their capabilities, and learning how to make them polymorphic for broader applicabilities. By making UDTFs polymorphic, we can tackle more complex data processing tasks with ease. Thank you.